Okay, picture here represents an experiment that we are going to do probably next week with a very sophisticated, expensive piece of equipment, a bottle with a cap and a tube sticking out. Okay, there's some water in the bottom of the bottle, which you could see if you back up the tape a little bit, back up the video. I'm going to set this up as if we have a cylinder representing the bottle. Doesn't have to be uniform size or anything, but arithmetic's easier if it's a cylinder. Um, and this is the water level. It's lots of calm water at a constant level. And this thing is sitting on the floor of the ocean or whatever this thing happens to be. It's calm, no waves, so we damped out all the waves. Well, in this case, Bernoulli's equation and other things and common sense and so forth tells you that if water is not flowing in or out of this container, then the pressure on one side of this opening is the same as the pressure on the other side of the opening, right? And the pressure above the opening, pressure due to the water above the opening, is equal to the pressure of the water above the opening on the other side. So the water level in here has to be the same as the water level out there. Okay? Now we put a lid on this thing so that it's now sealed, except for these little holes down here. Or maybe they're big holes, doesn't matter. Okay, so sun comes up and it heats up the air inside this or whatever gas is inside of here. What's going to happen? Talk about it for a minute. Okay. Matter of fact, you all are going to talk to each other about it for a minute. Response. Y'all didn't even need to talk to each other. He said, well, it's going to push the water down. Well, it's going to push the water down because molecules are being moving faster. And they're hitting the walls and they're hitting the water surface here faster. Okay. Now the pressure down here isn't going to change. It's going to be equal to the water pressure of the reservoir, which might be the whole ocean. It's a reservoir. There's enough water here that any water that gets moved in this process is not going to change the water level more than a molecular diameter. Okay. Insignificant change. Essentially infinite amount of water. Okay. So just draw this thing. Okay, here's the water level, which isn't changing, the water level of the ocean, which isn't changing. Here's the original water level in the tube, in the container before we put the lid on. We put the lid on, sunlight heats up, right? And what's that do? Well, if the whole thing is sealed, it's going to push some water out of this container, out of these holes, into this infinite reservoir. So that There's some heating. You got the new water level. Okay, so far, that's kind of interesting. Kind of interesting to be able to think about it and understand it and relate it to the kinetic theory and everything else. And also, you got T equals nRT. T is going up. Okay. Amount of gas in here isn't going up, right? Because no gas is escaping unless the water gets pushed down to this level. And then it's going to bubble up. Okay. Now we're going to add something to this system, which is a tall, thin, okay? And now we're going to heat it up again. What happens this time? Okay, we've had a discussion. Some people think water's going to go up the tube. Some people think other things going to happen. Okay? If we achieve this water level here by heating inside of here, if water went up the tube, just assume that water goes up the tubes. There's some water in the tube though. Okay? You have a pressure at the surface down here. Okay? Pressure up here has to be greater than the pressure down here. Between this point and this point, you have continuous fluid so that Bernoulli's equation holds, energy relations hold. Nothing is moving very fast, so the 1/2 rho v squared term is negligible. Okay? But you have a difference in altitude, difference in y or h, whatever you call the altitude. And you then have a difference in pressure. Altitude is greater here, so pressure is less up here. Because this is open to the atmosphere. This is an atmospheric pressure. Okay? So that can equalize the pressure between here and here. So that's entirely plausible. Okay? Now remember that the water that goes down can also flow out through these openings. Okay? So we'll leave that question of whether water actually flows out of the openings a little more complicated to think through. So we're going to have valves here that can be closed. So we close these things off before the whole thing starts. That makes sense? So just to be sure that water doesn't escape out of here, because what's really going to happen is you're going to have more pressure inside than you have outside if you get this situation. Okay. and water is going to tend to escape out here rather than rising all that high in the tube. So now water has no place to go but up the tube. Now, this is a thin tube, and I've drawn it a lot thicker than it really is. Just assumes a very fairly thin tube, okay? And look at how much water got displaced. That's a big chunk of water there, right? So all that water has to go up that tube. Now, there are two things that can happen. You can make the tube really high, so lots of water goes out. Or you can let water flow out here. You have some kind of a reservoir. Okay, it's not just floating in space. You might have some infrastructure there, but you're going to collect water up here that you can then release later to run a water wheel. So you're getting energy from the heating of the gas. That makes sense? Yeah. Okay, so it was observed. Again, if all this water filled the tube would have to be really high because it's really thin. Okay, so we're just using a thin tube to raise water to a reservoir here. So if this much water gets displaced, this much water is going to end up here, less whatever small amount of water it takes to fill the tube. Make sense? So by gaining heat from the air or from the sun or another source, we increase the pressure in here, depress the water, and raise it up here. And at some point, that's going to stop because the air only gets so hot. So the pressure only builds so high, water level. Now you got to build enough pressure, before you can start dumping water out, you have to displace enough water to fill the tube, which is going to take enough pressure to increase the pressure in here so that the pressure at the bottom of the tube, which is equal to the pressure of the gas, is equal to the pressure you get from the change in altitude. Okay? So that's your first cycle. First part of the cycle, fill the tube. And you can't just fill the tube. You can go up here and fill the tube, but it's all going to come down into here and, raise the water level in here just a little bit, increase the pressure a little bit. But if you have a source that increases the temperature here, you can pump a lot of water out of it. You can fill the tube, then you can pump water out. Now, start making a graph here. Versus volume. Now, I told you earlier, I'm pretty sure that the area beneath the pressure versus volume curve is work. Okay. And it's easy to see that in the introductory problem sets, I believe, do that. So we start at some pressure. All that P sub zero, P naught. We fill the tube. The tube is thin, very insignificant change in the volume of the gas. Okay, because what we're talking about is the pressure and volume of the gas. So we raise this up to pressure P1, right? Then the water's up here ready to flow out, and we keep increasing the volume of the gas. Okay. Now there's a very small increase in the volume of the gas here, but we're going to say it's negligible, and this is just a vertical line. Okay. If you want to give it just a little tiny bit of slope and calculate the ratio of cross-sectional areas and take all that into consideration, you can, but conceptually, it doesn't make any difference. As an engineering application, yeah, you're going to want to take account of a lot of different things, but here is what's going on. Here's the basis. As engineers, you tweak it. Okay? So what's going to happen now? The volume's going to increase. And the pressure is going to stay constant because pressure in here has been changed because of the altitude of water in the tube, and it's going to stay the same since the water's not going up the tube anymore. And that means we're going to be expanding gas and displacing it into the upper reservoir. So here we have V1. Now, at some point, the air reaches its maximum temperature and the gas stops expanding. Then what do? Well, maybe what we do is we equalize the pressure. Okay? That can be done in a couple of ways. Maybe you've got a valve up here and we just exhaust the hot air and let cold air come in. Okay? So we bring it back to its original temperature and pressure. Well, that'll typically happen by kind of quickly reducing the pressure. Okay? And then cooling the thing off. And there's a thermodynamic cycle. Yes. We've raised this much water. Okay. Using the force from this much pressure. So we've done some work represented by the potential energy change of the water that's now in the reservoir. So now you can completely analyze this cycle, right? Okay, well, let's move away from this whole system with water and stuff, although we are going to do an experiment, which is a soft drink bottle, some hot water, cold water, and see how much work we can do running a cycle of the system. Okay, the cycle is very simple. We dip the bottle into warm but not too hot water because we don't want to deform the bottle. Okay, about 150 degrees Fahrenheit. That increases the pressure, water goes up the tube and comes out, and we catch it. We can figure out how much potential energy change there was. Okay. Then we do it again and take the, tap the water at a different height and see where the optimal height is. And then I'll give you a little bit of information to allow you to compare the optimal height from what the theoretical optimal height ought to be, which is going to require a little calculus. Since we're going through this kind of quickly due to weather interruptions and the need to get on to other things, I'm not going to totally derive all that, but it's up there. I can tell you where to find it. Okay. Now, the cycle looks like this, and that's a typical thermodynamic cycle. There are other cycles. Look in your book, think about them. The question is, how do we release the pressure? Okay. We can bring the pressure back to the original by just opening a valve and letting gas escape. Okay. That would happen quickly. And there wouldn't be any time for exchange, it wouldn't be enough time for significant exchange of heat. Okay. That's called an adiabatic cycle. So you might want to make yourself a note of this. It's in the introductory problem sets. You should have seen it. Anybody tell me what gamma is? Just indicate if you know, and we'll stop talk about it. Gamma is Cp over Cv, where C is your specific heat. Non-atomic gas, Cv, is 3/2 R. R is just your gas constant, 8.31 okay, joules per mole Kelvin. Another number that you should know, or at least have written down for quick reference. Okay. Cp is 5/2 R. That's 1/2 R for each degree of freedom. It means to heat up a monatomic gas, you have to add energy to the X, Y, and Z directions of space, since you have independent kinetic energies in each of those directions. There's equal partition of energy. For a diatomic gas, as I demonstrated, or at least wave my hands over, you have 5 degrees of freedom, just for the benefit of the video, because I was out here and not in front of the camera when I did this. If you got these, they bounce around individually in 3 dimensions. They might have random directions, if that stands for molecule. This is a molecule. They can bounce around. They can move in the X direction, the Y direction, or the Z direction, any direction at all, okay? They can also rotate about this axis through the center or this axis through the center. These are perpendicular axes, and that's 2 independent directions in which they can have rotational kinetic energy. They don't have rotational kinetic energy about this axis. You just think about that. They aren't going to roll. But that's really not what's going on. It's deeper in the quantum mechanics and so forth, deeper than I can explain, actually. Okay? I mean, it comes out of the equations, but still. Okay? So that's why you got 3/2 R or 5/2 R. 1/2 R for each degree of freedom. 1/2 R for motion in the X direction, 1/2 R for the Y, 1/2 for the Z. And then you got a 1/2 for rotation about this axis and rotation about this axis, but not about this one. So it's easy to derive. It's pretty much derived in the introductory problem sets if you look at them carefully. Then I just gave you the wrong explanation. This is for a monatomic gas. I was thinking monatomic, diatomic, but I wrote it. Clearly, I could have looked at what I wrote. Let me just give you the diatomic. CV equals 5/2 R, and that's because of the 5 degrees of freedom for a diatomic gas. And CP 7/2 R. And the idea is simply that you got to add R constant for CP, because directly from PV equals nRT, you can conclude that you got to do RT, nRT of work to expand at constant pressure. Okay. In other words, if the water's going up here, your pressure is remaining constant, as we discussed. Once water's up here, what I say? Said your pressure is constant, and that's not correct. As water's going up, your pressure is increasing, right? So you got to be doing some work against the pressure. Okay. The gas is doing work to push down on the water here, and the water level does go down just a little bit and does enough work to get. Then the pressure remains constant. Okay. So, while pressure is doing the work, you got to have more energy. Okay, got to have more energy to do work against pressure. We're running a little short of time here. And that's why you add 2/2 of R to CV in order to get CP. You read that. You know, look again at what the introductory problem sets tell you. Hey, you can ask an AI. Don't let the AI take you to the level of quantum mechanics here. You don't have time for it, even if you really want to know it. Save it until you have time, which you never will, unless you're in that field. Okay. But AI can give you, I think, pretty good explanation. I think the explanations that you can pull out of the introductory problem sets, I got those right where I thought I wanted them 30 years ago. It seemed fit to change them since. Partly because it's a lot of work, partly because they pretty much say what I want them to say. And you have a textbook. Would scan it. You should know where things are in the textbook so you can look them up if you need to understand something. Okay. Anyhow, PV to the gamma equals constant. In an isothermal expansion, PV is constant. PV equals nRT. Okay. Isothermal means you're not changing the temperature. N isn't changing, R isn't changing, T isn't changing, so PV isn't changing, right? The work done, you have two integrals to tell you how much work is done in this expansion. If it's a diatomic gas, you would integrate P V to the 7/5 is CP over CV is 7/2 over 5/2. The R divides out, the halves divide out. You got 7/5. So gamma would be 1.4 for diatomic gas. It'd be 1.66 repeating for a monatomic gas. In an adiabatic expansion, for PV equals PV to the gamma is constant. Okay? So just figure out PV to the gamma in the original state. Okay? And then you can figure out what PV is, what PV to the gamma. Okay? What's the integral of V to the gamma? Antiderivative of V to the gamma with respect to V. Well, it's got to be a V to the gamma plus 1, right? Because you're going to take the derivative of it to get V to the gamma. You're going to decrease the degree by 1, right? But then, of course, the derivative of this is V to the gamma, is gamma plus 1 times V to the gamma plus 1. So you got to divide this by gamma plus 1. Okay? What's the integral? Oh, whoa, 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 whoa. I don't know. I must have got up on the wrong side of the bed. Um, wrote this down without thinking at all. But this would be nRT over V. And this would be P naught V naught to the gamma over V to the gamma. It's the integral of P dV, not the integral of PV dV. Because it's totally written visually with no mental process at all. And I apologize for that. Those are the integrals. So that the integral of you're just integrating a power function. It looks weird. It looked weird to me, so I think it's going to look weird to some of you. Okay? It's hard to get my head around just because the notation looked weird. So I understand how that can be. And the integral of nRT over V, the integral of 1 over V dV, it's a natural log of V. If you're going from V1 to V2, this should be from V1 to V2. And this should be from V1 to V2. just a simple natural log integral. But that could be handy. So what I want you to do is I want you to take your system, whatever volume you like, and figure out what happens in each cycle and figure out how much work is done in each cycle. You're going to have to refer to the introductory problem sets to some extent. Might have to refer to your text. But I've outlined the whole thing for you. So analyze as much of it as you can. Our goal is to figure out how much work you can get and how much energy has to be added to the system. You know, how much energy does it take to heat a cubic kilometer of air from 300 to 400 Kelvin? Constant volume, your specific heat is 3/2 R, which means about 12.5 joules per mole per Kelvin. Okay, you know what moles are? That's your N, and PV equals nRT. Okay, you figure all that out. You got everything you need. See how well you can put it together for next. See how much of it you can put together for next time, and I'll have you doing some discussion. Okay. Talk about some other things too, and see how much you can bring to the table next time. Okay.